Well, here's the idea. We figure, somebody's not going to hang around messing with stuff if they think their picture's just been taken. So we made this little box. Runs on a motion sensor with a little bright LED flashing. And as long as it detects motion around them, it'll repeatedly flash the LED. And this is made as a, crime deterrent device. Real handy, should run for a year or two on a 9-volt battery. So if you like it, we're going to show you how to make one of these. Okay, let's take a look at the innards here. Run on a 9-volt battery, and that's works because we have this 5-volt regulator which only draws 2 microamps on standby, so it doesn't drain the battery when it's not triggered. Here's the back end of the PIR sensor, which comes up with these handy 10th-inch center pins, which will take the standard DuPont connectors, so you get from here to there just with a jumper wire you buy. And there's the LED. So we had to solder wires to the LED, but then we bring it back here and connect it to our board that's got a big transistor here to give it a nice bright flash. Turns out it's a 6-volt LED on a 9-volt battery, and we only run it for 10 milliseconds, which gives a really bright flash and doesn't kill the LED. So that's the inside picture here. Okay, and here's our utility board, which we call Util 85D. Was our 4th version of this. AT Tiny 85. It's got a 5-volt regulator. There's 3 inputs, which are input output generic here, plus 2 possible high power outputs, power transistors. And we get these made, like 20, 30 at a time, snap apart boards, only populated with the parts we're going to need for a particular project. We're running on a 9-volt battery on this one, so we do need the power regulator. Otherwise, you can just feed the 5 volts directly in there or jumper across here when you make the board. Really handy. We use this in a lot of our projects. Okay, now let's get into the parts we use to make this device work. Here's one of our favorite parts for doing a lot of designs. The MCP 1702 is a lot better to use than the 78L05 regulator in the same size package. 250 milliamps of output, which is the 78L05, I believe, is only 100 milliamps. And this is the really good thing, 2 microamps standby current. And that's why we run a lot of our projects on a 9-volt battery, because we can leave this connected, and when we're not drawing power elsewhere, this thing isn't wasting any power. Goes up to 13 volts. It's also a low dropout. It's useful in places where the feed voltage gets down near 5 volts. The PIR sensor we bought in a little module with the pins, make it handy to hook up, and does have a 3.3 regulator, so you can run it on 5 volts. So here's the specs on the SP312, also sometimes called the BS312, so look it up either way. The great thing about this is the working current, which is in the order of 15 microamps, which is very useful for running on battery operated devices. When it's triggered, the 3-terminal device is non-adjustable and has 2.3 seconds digital output when it's triggered. So here's the current consumption on the ATtiny 84. Now when it's active, 8 megahertz, 5 volts, which is how we're running, we have about 4 or 5, maybe 5 milliamps expected. Now, but in the power down mode, the sleep mode, without the watchdog timer, we're only drawing a maximum of 2 microamps, which means probably maybe less than 1 usually, which is great for running on batteries. Okay, here's our circuit. This whole part here is one of our standard utility circuit boards, and these are the parts we added on the outside, which is a 9-volt battery. Powers this up through a regulator. It also feeds the resistor charging C2 here. The reason we do that is we want to put a huge power pulse through this LED to simulate a flash. So we use the capacitor, make sure we got a pulse of current. And the tail end of that goes down through one of our utility board's output transistors, which are fairly large. So all of this is run with a PIR sensor, 3-terminal digital output. When this is activated, puts a 2-second high pulse on its output line, and that's read in one of our inputs here, and we get into the software later. Okay, here's our source file, also available on our GitHub site. We're using one of our standard utility boards with a Tiny 85. This device uses a PIR sensor, puts a digital output, and utilizes the sleep mode of the ATtiny to save power. Might get into explaining some of this if you're not familiar with it. The C compiler hooked to the Arduino system is actually the GCC C compiler, which is a full feature C compiler, having all the features of standard C, including ones that Arduino does not document. Among them is the enum. You might Google this under C programming to see how it works. Basically, you can set up a bunch of variables in one statement. The first one's 0, 1, 2, 3, and 4. You can also make it start at different numbers instead of a bunch of defines. These are the pins on the ATtiny chip and what they're used for. Okay, and while we're using the main type system instead of the kind of hokey setup and loop things, because I like to write just real C programming. So this works fine. Set up all our bits with one instruction, because only the 0 bit, the detect, is the input, the rest are outputs. And here's the program cycle from here to there. It usually lands in the sleep mode. When it comes out of the sleep mode, it checks the detector bit coming in to make sure we're on the positive edge, not the negative edge, because we don't want it detecting when somebody leaves, only want it detecting when they arrive. So if that bit's still high, we do a flash for 10 milliseconds, and then we have to wait. This is 9,000 milliseconds. That's 9 seconds. The reason that's necessary is that the flash draws so much power from the battery that it upsets the voltage, which then makes the PIR sensor unstable. So we wait 9 seconds for the PIR sensor to restabilize. Otherwise, it's just going to keep triggering. And here's our sleep mode. Now here's our little flash routine. It simply sets a port bit, waits so many milliseconds, and clears the port bit. Okay, might as well explain some of this here. Bit set and bit clear are built in and are documented in Arduino. These are called macros. They actually compile to just a couple assembler instructions, but they're handy because you can name any variable, including a port, And the bit, well, the bit's defined up here as bit 0, 1, 2, 3. So this will turn the LED on, wait how many ever milliseconds we specified, then turn it off and wait a couple hundred milliseconds and return. Okay, what's wait? Well, we're not using the Arduino C++ stuff because I don't like C++, so we wrote our own little wait thing here. The delay microseconds is part of the regular C code, so that works. And all we do is we set the number, call with the number of milliseconds here. That's 1,000 microseconds. So this turns into a millisecond timer. Okay, finally here, how do we sleep? Well, the ATtiny has a sleep function. And you can, in their documentation, you can look up what all of this does. But briefly, you have to have the interrupt on change global bit enabled. Then this PC mask says which bit to change. Well, again, it uses bit set. This is the register, and the detect was defined as, up here, whatever. There, it's bit 0. All very tidy. We have to set the type of sleep to the total power down. Again, you'd have to look this up. That's how I get these. Then we have to enable global interrupts. And this is handy in case any other peripherals are drawing power. This shuts them off. Now, there's no sleep command in the Arduino C code. So we use an insert an assembler command to use the assembler sleep command. And when we come out of it, so at this point we're asleep, and we come out of it, we re-enable all the peripherals. It executes this interrupt here, which does nothing, and then continues on with the program, which is to go flash the deal. So that's it here. Like I say, it's available on the GitHub. We got a link for it. And that's how it works. Thank you. Okay, well, there we have it. I hope you find this a useful idea. And if you want to build it, we do have all the plans for actually even making the circuit board. But you can just wire it the same as that chip and put the software in, and it'll work just the same. So good luck to you there. If you're technical enough to actually try this project, which isn't exactly a beginner project, you're perfectly welcome to leave us a comment. You certainly get a response from us. So good luck to you. Have a good day.